Okay, good morning. This is Dr. B. This is planned to be the last video in this series. Today we're talking about statistics. Specifically, we've got a data set, a set of numbers, and we need to describe the data set. So working with the data set, we're going to use a very small data set here to illustrate some important principles. 1, 2, 3, 4, 5, 6. So n equals 6. We'll use n to refer to how many scores there are in the data set. If you're trying to make sense of this data set, the first thing, let's sort it. Let's get it a little bit organized. So I would always recommend rewriting the data set in order from least to greatest or greatest to least. Let's go least to greatest. So we've got a 23, we've got another 23. Often the data set will already be sorted for you. So we're doing this when they haven't sorted the data set for you. And we've got a 31 and a 32. 1, 2, 3, 4, 5, 6 scores. All right. So the first thing you might be interested in is how spread out the scores are. So you're going to learn about more sophisticated ways to describe how spread out the scores are later on. But the only one we want to talk about today is range. So range is just a simple idea about how far is it from the very smallest score to the very biggest score. Okay, so there are two ways to report out the range. I kind of like this way to say the range is 23 to 32. That communicates a lot of information. Technically, what they really expect you to do is treat it like a subtraction problem. How far is it from 32 to 23? 32 minus 23, we could call this the maximum score. We could call this the minimum score. If you subtract them, then the range is 9. If you're doing a standardized test or something like that, and they ask you what the range is for this data set, they expect you to say 9. I will usually talk about the range as being from 23 to 32. It kind of tells you about the 9, but it also gives you more information. All right. So one sense about how spread out the scores are. And then the other descriptive statistics are mostly what we call measures of central tendency. You're trying to give somebody a sense about where is the middle or the center of this data set. And there are the 3 M's: mean, median, and mode. All of them are different ways to give somebody a sense about where's the middle of the data set. The mean is the one that we'll talk about the most. It's kind of our gold standard. Let's get these other two out of the way. Let's start with mode. Mode is the most frequent score. And sometimes, if you have a big data set, sometimes the mode does a nice job about telling you what a typical score is. But other times, especially with a small data set, it can be pretty random and arbitrary. Like in this particular data set, we happen to have 2 23s, and that's the only score that we have 2 of. So in this data set, my mode, my most frequent score, is a 23. Now, in this case, 23 is not really giving you a good sense about the middle of the data set. It happens to be the lowest score. So modes are kind of unreliable. You can also have ties for modes. Like if I had 2 23s and also 2 27s, then I would have 2 modes. I'd have 23 would be a mode and 27 would be another mode. All right. Let's switch to medians. The median of a data set is you first put the data set in order from like least to greatest. We've already done that. And then you find the dead middle of the data set. So in this case, I've got 6 scores. If I go 1, 2, 3, and then 1, 2, 3, if I sort of think about right in there, between this 26 and 27, cuts the data set into the bottom half and the top half. We might call this the bottom 50% and this the top 50%. In this particular case, my median is going to be in between 2 numbers. I have an even number of scores, so I'm going to have to go in between these 2 middle scores. So in this case, I would go 26.5 would be my median. If I had another data set that only had 5 scores, an odd number of scores, then the 26 itself is the middle of the data set. So my median would be 26 there. But even number of scores going halfway between them. All right. So these two are useful, but most of my discussion and most of our focus is mean. So one thing to get used to is that elementary school kids have heard about averages. The mean is really just a fancier word for the average, okay? So to get a mean or the average of the data set, you take the total of all the scores and you divide by the number of scores. And that's going to give you the mean or average for the data set. In this particular data set, I think I already set it up so that they're going to add up to, well, let me go ahead and double check that. All right, so add up the scores. So 2 23s is 46 plus a 26 and a 27 and a 31 and a 32. There's my total. Divide by 6 scores. So 162 divided by 6, we've got a mean of 27. All right, this is the best indication about where the middle of the data set is. There are a few situations where the mean can be misleading, but this is our best. Each of these numbers contributed to the mean. If this one had been a little bit higher, my mean would have been a little bit higher. If this one had been a little bit lower, my mean would have been a little bit lower. So it's kind of nice because everything's contributing to this score. If you contrast that with the range is kind of is not as high quality a statistic, partly because it really only depends on 2 numbers, the very smallest number and the very largest number. And the range as a statistic ignores what's happening with all the middle numbers. So it's more limited, all right? All right, so this is one way to talk about the mean. I want to emphasize, and this is a good number sense activity, I also want you to think about the mean as a balance point for the data set. So if I go back and look at this data set, I've figured out that 27 is sort of the balance point. So I want you to sort of think these guys are below the mean and these guys are above the mean. This is the center. The center is a reference point. Where are all these other numbers with reference to the mean of 27? And a 26, you can think of a 26 as 1 below the mean. You can think of a 23 as 4 below and another 23 as 4 below. So the net effect over here is I've got 9 that are sort of pulling the mean to the left, pulling it down. And these guys, if 27 really is the mean, these guys have to be perfectly balanced by stuff that's on the positive side. So 31 is 4 more, and 32 is 5 more. So notice that this 27 is a balance between the 9 that's higher and the 9 that's lower. That's a very helpful way to think about the mean, especially if you're doing some manipulations and working with a small data set. So keep that in mind, that a mean is not just the total divided by n. You can also think of it as a balance point for the whole data set. All right. As a statistic, let's talk about the definition of the word statistic. A statistic is a number that describes a data set, okay? And different numbers describe different aspects of the data set. We've talked about these 3. These are each a statistic that's trying to give people a measure of the central tendency. We talked about a range. That's a statistic, that single number that gives you some information about the data set. Most generally, the kinds of statistics you have to work with fall into 2 main categories. You've got statistics like these that try to give you a sense about where the middle of the data set is. And then you've got another bunch of statistics, including range, that try to give you a sense about how spread out the scores are. Beginners, rookies, tend to focus only on these guys, okay? And that's important, okay? But don't forget that these guys are also important. Now, the only one you really have in your working vocabulary right now is range. But let's talk. So if I call these one category statistics, measures of central tendency, let's talk about this second category for a second about spread. I want to give you an example to illustrate that you need to think about spread also. We're going to look at two data sets. Here's one data set. These are very small data sets. Okay, it's just got 5 scores in it. If I'm trying to tell somebody how spread out the scores are, I would say the range is from 2 to 12, or the range is equal to 10. Okay, I have a second data set. It also has 5 scores in it. The range is from 5 to 7, so the range is much less. It's only 2. The thing that's interesting about these two data sets is that the mean, the measure of central tendency, also the median in this case, is exactly the same. If you add these guys up and divide by 5, this guy has a mean. This is a X bar, X with a bar over the top, is a statistical symbol used to abbreviate for mean. So whenever I write X bar, just think mean. The mean for this data set was 6, and the mean for this data set was also 6. So if all you communicate to somebody about these two data sets is that the average is 6, they're going to have very different ideas about what's going on. This is a very different kind of data set than this one. How do you communicate how different these data sets are? You tell them about measure of central tendency, but then you start talking about how spread out the scores are. And when you get to the more sophisticated ways to describe how spread out the scores are, it's always sort of in reference to the mean. Like, you know, you're thinking about how far is a 5 away from the mean? How far is a 5? How far is a 7? How far is a 7? Over here, how far is a 3? How far is a 2? How far is a 7? How far is a 12? All those better versions of describing how spread out the scores are sort of in reference to the center of the data set. All right, so just keep that in mind. You're going to have that idea will be a common theme as you do more statistics later in your math career. All right, so we have statistics that describe measures of central tendency, statistics that describe spread. The thing that we're missing is sort of a graphical visualization of the data set. And we need that to look at the distribution of scores. Okay, where are the scores? How you're looking at how spread out they are, and also is there a big lump of scores here and another big lump of scores here, or are most of the scores kind of in the middle of the distribution? Anytime you start asking questions like that, you're talking about the distribution of scores. It's hard to see the distribution of scores when you've got gigantic data sets or when you have just raw numbers like we had up here. So what people will do is they'll make a type of graph to allow you to visually see the way the scores are distributed. The most primitive version of one of these graphs is called a dot plot. To save us some time, I've gone ahead and made the graphs here. Okay, so we're looking at the distribution of scores in a data set, and we're using a dot plot. This might be a type of graph that you got introduced to in 5th grade. Our example here is going to be that in a 5th grade class, students were asked how many siblings they have. A sibling is a brother or sister. Okay, so if I look at this graph down here on the x-axis, along the bottom I've got the different number of siblings, and then each x represents a person in this class that applies to. So this x is Johnny, and Johnny has 0 siblings, means he's an only child. And this is Susie, and she was also an only child. So in this simple kind of visualization about the distribution of scores, each x represents a person or a data point or a score. So we've got 1, 2, 3, 4, 5, 6. We got 6 people who are only children. You space things out nice and evenly. 1, 2, 3, 4, 5, 6. You got 7 people that have 1 brother or sister. 3 that have 2, etc. Notice on 4 there's nobody that has 4 siblings, but there is one person that has 5 siblings. Okay. If I used, so we've got a graph that allows us to look at the data set and recognize that really most of the people are either only children or have one brother or sister. The range, these are statistics we talked about earlier. The range here would have been from 0 to 5. The mean is about 1.4, but if all I told you was the mean of 1.4, there's a lot of things that you don't really have a feel for about this data set until you look at the distribution of scores. This had 19 students in it. Okay, so with really simple data and nice, clean, easy numbers like 0, 1, 2, 3, 4, 5, you can just use something called a dot plot, and this is an example of a dot plot. Okay, the higher this stack goes, the more people are in that category. Once your data sets get more complicated and the numbers aren't so clean and easy as 0, 1, 2, 3, 4, 5, or the data set's much larger, then you go to a more advanced version of a dot plot that we call a histogram. So this is going to be your first example of a histogram. All right, we're looking at the distribution of scores. It's serving the same purpose as a dot plot. But we're going to do it using a histogram. A histogram is a lot like a specialized type of a bar graph. You've got bars going up. In a histogram, the bars are touching each other, bumped up against each other. In a traditional bar graph, you'd have gaps. So this particular data set is showing us the grades in one of my advanced math classes. Okay, and this is a realistic situation in case you're curious. So these are their grades at the end of the year. What we can see is by the height of this bar, we had most people were in the 90 to 100 range. So that, in other words, these people are making A's. 80 to 90, these people are making B's, these people are making C's, and these people are making D's. Okay, the height corresponds to the frequency. So over here on a histogram, also on a dot plot, this is how often something occurs. So the y-axis, x-axis, y-axis, the y-axis in a histogram is always representing how frequently something happens. So the taller the bar, the more common it is. So in this particular class, I had 14 A's. The B's were the next most common. I had 8 B's. I had 3 C's, and I had 1 D. Okay, my range was 63 to 100. My average was 89, and there were 26 people in the class. My point on distribution is a lot of students don't really sort of distribution. That's kind of a waste of time. If this is all the information you had, you wouldn't realize lots of things about this data set. You wouldn't realize that more than half of the class got A's. Okay, you might not realize that there's only one I think there were like 4 people who got C's or below. Okay, once you start looking at the distribution, you have a much better understanding about what the data set is. So descriptive statistics in combination with looking at the distribution is your starting point for getting a sense of a data set. This is an unusual data set because I had my greatest lump of scores here on the far right. Okay, let me show you another situation which is a more typical data set in terms of what the distribution looks like. So we call this kind of a distribution a normal distribution. And in this example, we're looking at the times for 5th graders to run the 100-meter dash. The gym teacher had everybody run a 100-meter dash and he recorded their times. All right, so we're measuring the time in seconds. And we're presenting the results in a histogram. Okay, so I mean, some people are going to have times like 17.8 seconds. So what you do is you pick an interval. Like I chose to use intervals that were 2 seconds wide for this presentation. In another situation, I might choose intervals that are 5 wide or 10 wide or 1,000 wide. Okay, So you're choosing some useful interval to help you present the data. I chose 2 seconds at a time. So these are like bins. I'm putting everybody that was in the 18 to 20 second in this bin right here. Okay. It's still a histogram. We still have bars. The bars are still touching. It's still frequency on the y-axis. Okay. So this is more typical because when you have a collection of data, you usually have most of the scores kind of at the center of your distribution. Okay. And then as you get higher than that average, it tails off. And when you get lower than the average, it tails off. So you end up with sort of a bell shape or a mountain shape, okay, where you've got most of the scores in the middle, and then you go this way and they start dropping off, and you go this way and they start dropping off. That's what we mean when we call a distribution a normal distribution. Many kinds of data that you collect, once you graph it, it ends up looking something like this. So what we have here is the most common time for this 100-meter dash was in the 24 to 20 second range. Okay, to borrow from the idea of mode, which is most frequent, sometimes we would call that a modal interval. It's not that a single score is the mode, but the 24 to 20 second interval is our most common interval. So we can call this our interval mode, modal interval. Okay. And then if you get slower than that, it's dropping off in frequency. If you get, these are the people that are running slower, these are the people that are running faster. And it drops off in both directions. We call this the tail of the distribution, and here's another tail of the distribution, and we call this the center of the distribution. Okay? So lots and lots of data you're going to get are going to have that sort of mountain bell curve type shape. All right, let's look at one more example in which we're trying to appreciate the value of looking at distributions. And I'm going to change my scale here a little bit. There we go. Now we can see everything. All right. So this is a data set in which 20 fifth graders and their dads were measured for height. We're measuring it in inches, so just as a reference point, 5 feet is exactly 60 inches. 6 feet is exactly 72 inches. So 20 fifth graders and their dads, so our total data set had 40 scores in there. The shortest person in this whole data set was 45 inches. So that's about like 3 feet 9 inches. You can think about where you would have shown up in this data set. The tallest person in this data set was 78 inches. That's 6 feet 6 inches. The average for everybody, this is something I want you to think about. The average for everybody was about 60 inches, so that's about 5 feet tall. Okay, that's the average. All right. So now let's look at the distribution of scores. Okay. In this case, I chose to make my bins, my intervals, 5 inches at a time. So anybody that was anywhere between 45 and 50 inches went here. Anybody between 50 and 55 went here. All right. So look at the shape of that distribution. Okay. It's kind of got an interesting shape. It doesn't have like a normal distribution. Okay. It like goes up and then it dips back down and then it goes back up. So it's kind of like if this was a camel, it would be a bicamel camel, meaning a two-humped camel. So what we have is this kind of distribution is called bimodal. It's like there are two areas where you have lots of scores. I've got lots of scores in this 50 to 55 range, and then it drops off. And then later on, I've got lots of scores in this 70 to 75 range. Okay. Now, if you think about where this data set came from for a moment, hopefully it shouldn't be too surprising that you ended up with this kind of a distribution. What's going on here is that these heights are most of the fifth graders, and these heights are mostly their dads. Okay? So think about how misleading saying that the average height is 5 feet would be if you're trying to describe this data set. In reality, there's almost nobody. Here's 5 feet right here. there's almost nobody that's 5 feet tall. There's a bunch of people that are shorter than 5 feet and a bunch of people that are taller than 5 feet. And if you mash everybody together and average them, the average turns out to be 5 feet. But 5 feet is not really doing a good job of describing the people in this data set. Okay? What does give you a sense about what's going on is to look at the distribution of scores in a histogram like this. All right? And that's it. Those are the main themes. Those are the main issues of statistics that we want to cover in 6th grade. If this is your last video to watch, congratulations. I hope it was valuable to you, and I'm looking forward to seeing you at the end of August.